Hello and welcome to this discussion on vector fields and in particular Leigh brackets. So last time I defined this operation starting with two vector fields. So the main definition is here. Notice that one actually needs vector fields. Tangent vectors will not do, because I need to get a function here on the manifold in order to act xp on that, and in order to get a function, well, I have to have y defined at all points on the manifold. So now let's check, let me quickly start checking the derivation property of this. I won't complete it, it's fairly straightforward. So what does it, so what do we have to check? No, before I start checking, I should write the second part. Second thing is that xy is smooth. In other words, it is indeed what we call a vector field. As p changes smoothly, this xy changes. So to check, let fg belong to C infinity m. So what I want to do is I want the Leibniz rule to hold. So I want xyp acting on fg. We want to verify whether this is f of p xyp acting on g plus g of p xyp acting on f. So this is so let's say that I'll put a question mark here. Is this equal to the right hand side? So it's just a matter of going through the definition. So for instance, the left hand side, the LHS equal to xpy. Now the function here is fg minus yp x fg. Now here when y acting on fg, so let's look at this y acting on fg. Now the point is this is a function on the manifold. So let's see its value at any point x is yx acting on fg by definition. And now this is once I take an x, this is a tangent vector, and then I use the derivation property for this. So this would be f of x yxg plus g of x yxf, which I can write as now. So if I don't want to mention x at all, this of the above equation amounts to saying that y of fg equal to f, this function f, multiplied by y of g plus g multiplied by the function y of f. So we can use this without mentioning x. So instead of yfg, I put f times yg plus g times yf. F times yg plus g times yf. And similar thing here. So I won't complete the calculations. It's fairly straightforward. So you do a similar thing here. Then you again use the derivation property of xp. So here that will give me 2 terms here. So altogether there will be 4 terms coming from this one, this, and another 4 from this. One combines the appropriate terms and writes it in this form. That's it. Notice that some cancellations will also take place, and then one gets what one wants. So now, as for smoothness, if one uses the definition of instead of using local coordinates, one just goes by definition of smoothness. One has to look at this xy. So the function, this function for any f in C infinity m. So this is what I've sometimes called gx equal to this. Smoothness, one just looks at this, and this by definition is x at x, y of f minus y at x, x of f. Now, since individually x and y are smooth vector fields, this thing here is a smooth function, and so is this thing. Yf and xf are smooth functions. Again, the fact that x is smooth will say that this is also a smooth function where the variable is x. Likewise this. So overall you get a smooth function. So it's quite straightforward. So let's look at some examples of Leigh bracket. Oh, when I was one brief remark, when I just checked the Leibniz rule property, but linearity is even more clear. So here linearity with respect to the function f. If I take 2 functions, add them up, f and g, then it's clear that the right hand side is linear as well. So the Leibniz rule is the only thing to check there. Now, as an example, let's just take a trivial thing but very important example. So let U contained in Rn. Actually, I don't even need the open set. Let me take the whole manifold on Rn. If x equal to del by del xi, y equal to del by del xj, other 2 basis vector fields, then let's see what xy is. Xy acting on f would be x is del by del xi at a point P. So let's say del by del xi at P acting on y of f. Now y of f is just del f by del xj minus del by del xi del by del xj at P acting on del f by del xi. But this thing, both these are what one usually denotes by mixed, what one usually means by mixed partial derivatives, and they're denoted like this: del squared f by del xi del xj at P minus del squared f by del xj del xi at P. And we know from multivariable calculus that mixed partial derivative for a smooth function, mixed partial derivatives are equal. So therefore this is 0. So if we start with any 2 elements, any 2 vector fields, the standard vector fields, namely partial derivative vector fields, the Leigh bracket is 0. Well, the significance of this I'll come back to later, but for now I need one proposition relating, so let f from M to N be a smooth map suppose x1, x2 are two vector fields are f related to y1 comma y2 on N. Then the Leigh bracket of x1, x2 is f related to y1 comma y2. So this the notion of f related ties in nicely with this Leigh bracket property, and the proof is again a straightforward computation. So here, so what, it's just a matter of knowing what one has to check to say that this is f related to y1, y2 amounts to saying, checking the following. Let phi be a C infinity function on N. Then we are asking the question if df dfp of x1, x2 at the point P act, so this acting on phi is the same as y1, y2 at the point. Now DFP of this f related amounts to saying that this is the same as f of p acting on phi. So again a question mark here. So this is what we are trying to verify. So let's see how it goes. Now this the left hand side is equal to, by definition of the differential of a smooth map, this is the same as x1, x2 at P acting on, well, it is phi composed with f. Now I'll use the definition of the Leigh bracket. So this is x1 at P. Actually, yeah, it's somewhat inconvenient to retain this P. X1 at P, x2 of phi composed with f minus x2 at P, x1 of phi composed with f, and then this brackets. So now I know that it's just a matter of now unraveling the various hypotheses. So for instance, x2 is f related to x2 f related to y2. This just means that df of x2 at the appropriate point is equal to y2 at the appropriate point. So if I actually act it on some function, So in particular, so x2 df of x2. So right, if I act it on a function which I called the function phi, df x2 acting on phi equal to y2 acting on phi, and this would be the same as, well, it's x2 acting on, actually f composed with rather phi composed with f. So in short, x2 of phi composed with f is just y2 of phi. Everything has to be considered at the appropriate points. So for instance, right, so if x2 is at p, then y2 would be at f of p. So here this would be y2 phi at composed with f. y2 phi is a function and I'm evaluating it at f of something. So this is like this, minus x2 of p. Same thing with x1 and y1 will give me this. Again, go back to the definition of differential of a smooth map. This would be df of well, x1p acting on the function y2 phi. Similar term here. So I'll just write. So here, just to be clear, I'll just put dot dot dot. So you'll get a corresponding term on the other thing. So let me just focus on one term, simplifying one term. So that will be, and finally, well, what is, yeah, again I use the fact that, right, so this is actually at p. So this would be y1, the fact y1 at f of p, y2 phi, and the second term will turn out to be y2 at f of p, y1 at phi, which is by definition the Leigh bracket of y1, y2 at the point f of p, which is what I wanted. So this is what I wanted and I get that. So one has this very important and useful fact that f-related vector fields go to f-related vector fields under the operation of Leigh bracket. So in particular, one corollary of this is that in a coordinate chart, the coordinate vector fields have pairwise Leigh brackets 0. So remember that for us coordinate vector fields, so this, if this is a coordinate chart to something in Rn, on Rn at each point we have this del by del xi. We have the local, we have a frame on Rn. So we have del by del xi here at each point. And when we pull this back to the manifold via this using the diffeomorphism phi, we get vector fields on this open set U, which we called coordinate vector fields. So the coordinate vector fields are by definition coordinate vector fields on U are basically at the point P. If I start with a point P, I just look at, so let's see if x1 equal to, so I look at the corresponding point del by del xi, del by del x1 at the point phi of P. This is the here, and then use the phi inverse derivative of phi inverse d phi inverse at the point phi of P. So this is x1 at P, what I've written here. So we have seen this many times before, the usual. Right, so here the thing is that this x1 at x2 etc. are phi inverse related to del by del xi. Xi is phi inverse related to del by del xi. I just wrote the x1 equation here, but so this is just the very definition of this coordinate vector fields shows that they're related like this. Since we already seen that the coordinate vector the standard partial derivative vector fields have Lie bracket 0, the same result holds for this xi's as well. Now let us see what the Lie bracket looks like in a Lie bracket in a coordinate chart. I'll fix a chart U phi and then so I'll just take two vector fields x and y on M. We know that, as just talked about in the last page, that on U we have this frame, in other words n vector fields x1, x2, xn, which form a basis for the tangent space at each point of U. Therefore, I can write, as we have done earlier, x equal to ai. I should mention one thing. So I'll follow the usual convention. So instead of writing this x1 etc., I'll just use del by del xi here as well. So del by del xi is used for on Rn as well as on the manifold. On the manifold, what we actually mean is d phi inverse of del by del xi. So I'll write it as del by del xi and then y equal to some other function like this. So here I equal to 1 to n, j equal to 1 to n again, and this ai and bj are both functions from C infinity, functions from U to R. So let's see what this is. So xy so before I proceed, let's make a few general comments about the algebraic properties of Lie brackets. So let algebraic properties of the Lie bracket. What I need here is that it is what is called bilinear in both input variable. So in other words, if x, y are two vector fields on M, and if you have two real numbers a, b. Actually, I need right. Let me take three vector fields. If x1, x2, y, and then a, b are two real numbers, Leigh bracket of ax1 plus bx2 y, bx2 with y is the same as ax1 y plus bx2y. Similarly, x, y are two vector fields, then the Leigh bracket of xy is the negative of the Leigh bracket of yx. So this will automatically, if I combine this and this, 1 and 2, I see that the third property, even in the last second slot as well, one has linearity like this. So 1 plus 2 implies if x, y1, y2 are three vector fields and you have two real numbers, then x a y1 plus b y2 is equal to a x y1 plus b x y2. Now there is actually these are the trivial properties. There is something more unexpected which happens here, which has to do with three vector fields, which I won't mention it now. For now, let's just use these and simplify our calculation. Go back to this coordinate chart. So in the coordinate chart, I had this. So this I can write as Leigh bracket of summation of ai del by del xi summation bj del by del xj. Now I can use the linearity in the, so if I have sum of two vector fields, and if I keep the y thing fixed, I have a splitting like this. So that's what I'll do here. First I'll write it as summation over I Leigh bracket of ai del by del xi, then this is kept fixed, bj del by del xj j. Then I'll keep this del by del xi fixed and then expand it over that. So summation over I comma j ai bj, and then oh sorry, yeah, well, these are not for constants. This holds only for constants. So here I can't take out this ai, so I have to keep it inside the so here what one gets is right. So summation, and then the ai will stick with this, and similarly here this one can't take it outside. So here what one gets is ai del by del xi comma bj del by del xj, both within brackets. And in my next lecture I'll simplify this and we'll see. It's it's just mainly for computational purposes. It has no special significance, the expression that we are going to get. and then I'll talk a bit about Leigh brackets of left invariant vector fields. Okay, thank you.